Hello and welcome back. So it's been a while since we last talked about complex integrals, and thank you for your support during this time, and I apologize for the delay. In this particular video, let's talk about a very important theorem known as Cauchy's integral theorem, and see how some of the discussion that we've been having so far leads us to an understanding of this theorem, leads us to actually proving this theorem. We'll use some of the ingredients we've talked about so far, in particular from vector calculus and the interpretation of a complex function as vector fields in the complex plane, and see how sort of that enables us to easily understand and prove this theorem. So without further ado, let's first state what this theorem is, and then we'll talk about the other aspects. So Cauchy's integral theorem states that if a complex function Wz, so if Wz is a complex function, and if Wz is an analytic function, Wz is a complex analytic function, that is a complex analytic function defined over a simply connected region of space in the complex plane, defined over a simply connected region. We just denote this region with the symbol R. So if it's a complex analytical function defined over a simply connected region R of the complex plane, and C is some contour or a closed loop in this region of space. So and C is a closed contour in this region of space, then the integral of Wz dz over this closed contour C is 0. So in other words, let's assume that this blackboard is some simply connected region of space in the complex plane, and we'll talk a little bit more about what a simply connected region means in a future video. But for now, the kind of discussion we've been having so far in terms of a well-defined, let's say, a simple part of the complex plane, and where we take a loop closed contour which perhaps looks like this, a closed contour C like this, then this theorem states that the integral of any analytical function Wz, any function which is analytic over this in this particular region of space over this closed contour C is 0. And this is a very, very powerful theorem because it doesn't talk about what particular function Wz is. All it says is that Wz needs to be analytic in this region and over this closed contour C. As long as it satisfies this condition, its integral over the contour is 0. Now, one consequence of this, and I put a link to one of the previous video where we talked about this part. One of the consequences of the vanishing of this closed contour is that let's say we have 2 points in the complex plane, Z1 and Z2, and we make a loop something like this with and denote this loop with the symbol C, which basically turns out to be our contour C. However, let's focus on these 2 points, Z1 and Z2. Now, if we are saying that the integral of the complex plane over this entire closed contour is 0, what this also means is that if we break this contour into 2 parts, C1 and let's say part C2, such that an integral over C1 goes from Z1 and Z2 along this path, and an integral over C2 goes from Z1 and Z2 along this path, and C is defined as C1, part C1 minus part C2, and I'll put a link to one of the videos where we talked about this. Then basically what we are saying is that we can break this integral into 2 parts. The integral over C1 minus the integral over C2. And we're saying that this integral is 0 as long as WZ is analytic in this region of space and on this contour C. Or in other words, if this expression on the left hand side is 0, what this means is that we can take this part of the expression on the right hand side and rewrite this as follows, that the integral of WZ over C1 is equal to the integral of WZ over C2. And C1 and C2 are any general paths. We haven't made any assumptions about these paths either. So what this tells us is that Cauchy's integral theorem, as a consequence of the Cauchy's integral theorem, if WZ is analytic in some simply connected region of space R in the complex plane, then its integral from point Z1 to Z2 is independent of the path of the integral. And this is one of the things that we talked about in one of the initial videos, is something that we're looking for. We're seeking to find out conditions where this integral is independent of the path. And indeed, we have found this condition now. We're yet to prove it, but the condition according to Cauchy's integral theorem is that as long as WZ is analytic, its integral from Z1 and Z2 is independent of the path, which also means, so the integral is path independent. And this also means that just like for functions of one real variable, if we try and integrate functions of one real variable, we are able to define an antiderivative of that function. In the same way, if the integral of a complex function is path independent, we can actually think about defining antiderivatives of this function. So this means that we can define the antiderivative of complex functions and complex analytic functions. Antiderivatives of complex analytic function. Right. So now, so we'll think about some of these ideas again in future videos by means of examples. But for now, let's try and prove the Cauchy's integral theorem using some of the things we've already talked about in the previous videos, and then we'll talk about specific examples in future videos. So let's try and prove the Cauchy's integral theorem, and for this we need 3 steps essentially. As a first step, again I'll put a link to the previous video where we talked about this. Let's consider the integral of a complex function WZ dz. We've already talked about how this integral can be written as the work done by a dual vector field E tilde plus I times the flux of this dual vector field E tilde. And here, by E tilde we mean, let's say WZ is the complex function with real part U plus imaginary part V, then E tilde is a vector field which has its x component as U and its y component as minus of V. And again, I put a link to the video where we talked about this part. So this is the first step, that the complex integral along some path C, we haven't yet focused on closed contours, we'll do that in the next step, but along any path C in the complex plane can be written as the work done along that path and the flux through that curve of a dual vector field E tilde. So with this in mind, the second step is, if we are now focusing on closed contours, C, if C is now closed contour, then this integral, by virtue of the definition of work done and flux in a closed region of space, again this is something we derived in the previous video and I'll put a link to that video, the work done in a closed region of space can be written as the curl of the vector field E tilde through that region of space. So we can write this as del cross E tilde dA plus the flux can be written as the divergence of the vector field E tilde through the region of space. So del dot E tilde through dA. Okay, so that's the second step. Now as a third step, so I just erase these parts for now. as a third step, let's calculate what del cross E tilde and del dot E tilde are. So if you recall, del cross E tilde is essentially the curl of, so del is again a symbol which comes from using partial derivatives along x and partial derivatives along y. So what we want to calculate is the curl of the vector field u comma minus v, and this is nothing but minus dv dx minus du dy. Similarly, the divergence of the vector field E tilde is the dot product of the partial derivatives along x and y with u comma minus v, and so this evaluates to du dx minus dv dy. Right? So what we are now saying is that so I'll just retain these two expressions for now. So what we're now saying is that the integral of wz along the closed contour C can be written as the work done, which in terms of partial derivatives evaluates to minus dv dx minus, rather plus du dy, because we've taken the minus, common minus sign outside, plus I times the flux, and the flux is du dx minus dv dy. Okay, so from the second step, we've arrived at this particular condition. So we've expressed the complex integral in terms of partial derivatives of u and v in that region of space R. And as a third step, the Cauchy's integral theorem, recall that the Cauchy's integral theorem states that if wz is an analytic function. So where does analyticity come into picture now? Now if you look at the forms of these expressions, these are, perhaps you remember something we've talked about before, and that is the Cauchy-Riemann conditions. So if wz is an analytic function, if wz is an analytic function, if wz is analytic, then the Cauchy-Riemann condition states that, according to the Cauchy-Riemann conditions, and I'll put a link to the video where we talked about this, states that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y is minus of the partial derivative of v with respect to x. Right? So if wz is analytic, it satisfies these conditions. And if you look at these, the forms of these expressions, we see that if wz is analytic, then du dx should be equal to dv dy, and therefore this is 0. Similarly, du dy should be equal to minus dv dx, and therefore this term should also be 0. And the net result is that the integral of wz dz is 0. So we have shown using all the ingredients we've been talking about so far that if wz is analytic in some simply connected region of space R, then indeed its integral over a closed contour C is 0. In other words, it also implies that the vector field associated with wz is sourceless and irrotational in a region of space where wz is analytic. So this is one of the most important, perhaps one of the most important theorems in the study of integrals of complex functions, and hopefully you see how some of the work we have been doing so far in reviewing vector calculus, in building up the idea that a complex function can be represented as a vector field in a complex plane, helps us give good insight into the physical interpretation of Cauchy's integral theorem. And in the next parts of the videos, we'll work with specific examples and build on these ideas further. So hope this was of some use, and hope to see you soon again. Thanks for watching.